All right, so let's quickly dive into this. Tonight's topic, floating point numbers. So floating point numbers is a way of representing decimal points, right? Because you have numbers that are whole numbers, so which means 1, 2, 3, up to infinity. But however, once you have something that's less than 1, it's a fraction of a 1, then you need to have a decimal point to represent that fraction of a number, right? So that's what floating points are. They're very easy to spot in programming languages, right? Any number that you type has, like, as long as you put a dot in there, it instantly changes from an integer or short or long and gets automatically converted into a float. Okay, so what's a float? So float, on top of just representing a decimal point, we have just like the positive and negative. There's no sign bit that says this represents positive or negative. You have to use zeros and ones to do it. Same thing with decimal points. There's no representation of a decimal point inside your computer hardware. So it also needs to be represented using zeros and ones. So in order to represent it, especially since a decimal point can move around, right? Because the decimal point isn't always in the same place. That's why it's where it's floating point. The word float means that that point floats around, and you have to just specify where that point belongs. All right, so we're gonna cover the specifications for encoding a single precision float and a double precision float. So let's quickly talk about some of the consequences or characteristics of floating point encoding. Is that by using a floating point encoding, you're able to represent a wide range of numbers, wider than an integer. Okay, so what does that mean? That means that on top of just representing very small fractions, you can also represent very large integers. So it doesn't have to be just fractions. Using the floating point encoding, you're able to represent just integers, and you can represent very large integers, much larger than a regular int. All right. Next thing is range is limited by the number of bits. So what does that mean? That's designed to work in conjunction with a third point, precision and range. Is that given a number of bits, you can represent a specific set of numbers. However, we can represent a larger range of numbers if we're willing to trade in precision or give up precision. So precision is defined as accuracy of representation, is how accurate you can represent a specific value. All right, so we'll actually go over details and give you examples just so you can see exactly what I'm talking about. So let's just quickly dive in now. So with floats, when you encode a number, let's look at the number on the left. That's 3,155,760,000. The number on the right is the same value, right? But however, it's written as 3.155760000 times 10 to the 9. They both are representation of the same value. Again, remember going back to the difference between number and value. Both of these represent the same value. However, they're written differently. On the left, you just have the whole thing written out like a base 10 number, but on the right, it's written in what's called scientific notation. So you have 3.15576 times 10 to the 9. Okay, that times 10 to the 9, this exponent, let me highlight this. Oops, why is this not? There we go. This is the exponent. So what's the purpose of this exponent, this times 10 to the 9? Well, the exponent is essentially times n. Guess what n is? N is your number base. So if this is base 10, it's going to be times 10, right? And then your exponent is up here. So the e or exponent is how many positions to move the decimal point. So looking at this example is times 10 to the 9. So if I want to know how many positions move the decimal point, 9 means move it 9 places, which is over here. Okay, so that's 9 positions to get the value, and that will give you the number on the left. Okay, so that's base 10, but you can use scientific notation also for base 2, right? So when you're doing binary, then it's scientific notation is not times 10, it's going to be times 2. And so this tells me that I need to move it, the decimal point, 2 places. So the decimal point is right here. Then if this is 1001, 00, and then decimal point, because it had to move 2 places. Okay, and that's why you get this number right here. All right, everyone got this so far? So scientific notation, it's really a good way of identifying or moving that decimal point. That's telling you where that decimal point needs to be. So with that being said, let's take a look at some representations. Given a base 2 scientific notation value, there's technically an infinite number of representations for it. So you see the number at the top, 1, 0, 0, 1, 0, 0, 0 times 2 to the 0, right? This value. All the numbers beneath it, these all represent the same value. Does everyone understand this? So all of these represent the exact same value. They're just written differently, but they all represent the same value. So because there's an infinite number of representations, well, we need to figure out which one are we going to encode, right? So the one that we're going to encode is the one representation. There's only one representation where there's exactly a 1 to the left of the decimal point. All right, give you a few seconds to sink in. I can give you an infinite number of representations for a number, but only one of them is going to have a 1 to the left of the decimal point, other than 0. Okay, other than non-zero. As long as it's not 0, every non-zero number has exactly one representation that has a 1 to the left of the decimal point. So with that being said, the encoding that you want to do before you can actually encode it needs to do what's called normalizing the number. All right, so we're trying to normalizing the number means I am going to write the binary number into scientific notation in a format where there's exactly one digit to the left of the decimal point. And that's called normalizing it to one digit. Does that make sense? All right, so now give you guys an exercise to do. Here are 4 numbers. I want you to normalize all 4 of these numbers to one digit. Give you a few minutes to work on this.
Can you go back to the last slide for a second?
Okay.
Thank you.
Done?
Yeah, I'm good. Thanks.
Okay, so have at it. Normalize these 4 numbers to one digit. All right, so let's do this together. All right, so this first one is times 2 to the 1, right? So you want to move the decimal one place. So this becomes 1, 0, 0. Oh, I'm sorry, my bad. Mix the problems up. All right, so what I want to do is I want to move the decimal point over here, right, to normalize it. So how many spaces is this? 1, 2, 3, 4, 5. Okay, so I want to add 5 to the exponent. So it becomes 1.001 times 2 to the 6, right? It's 1 plus 5, 6. The next one is how many spaces? 1, 2, 3, 4, 5. 5 spaces, so 4 plus 5. So this is 1.1101 times 2 to the 9. The next one, I'm going to move 1, 2, 3, 3 spaces. So this is 1.0101 times 2 to the 6. All right. Now, last one is a little trickier because it's moving the other direction. So the decimal point needs to move 2 spaces, right? So this is now -2. So it's going to be 1.001 times 2 to the 2. All right. Any questions? All right, so no questions. So now once you normalize it, that was actually one of the toughest parts, is normalizing the number.
Explain this again.
I'm sorry?
Can you explain this again, the number 1 and number 2?
The first and second one? Okay. So I want to normalize it. So by normalizing means I want to move the decimal point from here to here, right? So how many spaces is that? This is 6. 1, 2, 3, 4, 5. It's 5 spaces, right? So you take the exponent 1 plus 5, and that's how you end up with 6. You got it?
Yes.
Okay. All right. So now let's take a look at, once you have it set to a normalized to 1 bit, this is where you start encoding it into a floating point number. So a floating point number, assume it's 32 bits. All right, a single precision floating point has 32 bits. You have a sign bit, you have an exponent, and you have fraction. But when you encode it, this is the fraction you want to encode. Okay, I'm just change the colors. This is your exponent, would be over here. Okay, and then you're going to have a sign bit for 0 or 1 for positive and negative. So notice the one thing I didn't highlight is, put this in purple, is this. I didn't highlight that. I highlighted it because, for a reason, is that since there's always going to be a 1 to the left of decimal point, actually that's what I wrote here. Let me highlight this. Because by definition, if you normalized it, there's always going to be a 1 to the left of the decimal point. So because it's always going to be a 1, we're not going to waste any space encoding it. So,
but then how do you encode 0?
I'm sorry.
But then how do you encode 0 in a floating point if it always starts with 1?
Well, we're going to cover that.
Okay,
That's one of the special cases. All right. So everyone got that? Is because if you normalize this, there's always going, if you do this correctly, let me rephrase it. If you do it correctly and you normalize it, there's always going to be a 1 to the left of decimal point. And because the computer scientists were always very clever guys back in the day, they said, hey, there's only 32 bits. Let's not waste one of the bits. If it's always going to be a 1, then why are we going to waste a bit encoding if it's always going to have the same value? So we don't encode the hidden 1. Okay, again, that's why it's called a hidden 1, because there's no need to encode it. All right, so that said, let's take a look at the specs. So the first bit of a float is going to be 0 for positive and 1 for negative. So that's just like 2's complement. The exponent is 8 bits. So easy way to remember the range is to remember the exponent can be everything except all zeros and all ones. So you can do everything else except all zeros and all ones, because those are going to be the special cases that we're going to cover later tonight. All right, so there's two special cases. When one where the exponent's all zeros, and the other is when it's all ones. So the exponent can be anything except all zeros or all ones, and it's encoded using excess 127. So remember what that means? That means that, remember this chart, we just always create a table, 127 to decimal. That means binary 0 corresponds to negative 127. Okay, so this is one of the places where we see that encoding that we talked about a few classes ago. All right, so the remaining things on here is, once I have a sign bit and exponent bits, I have 23 bits left. So the 23 bits is used to encode the fraction. However, remember, I don't need to encode the hidden one, so it's everything else. So it means everything after the decimal point gets encoded. All right, so that being said, let's look at this example. So given this number there, 1, 0, 1, 1, 1, 1, a whole bunch of zeros and ones, what is the value there? So so we break it apart. The first bit is your sign bit, right? So we know that 1 means it's negative, so it's negative. Then let's do the next 8 bits is the exponent, right? So the exponent, we got to figure out what is the value stored there, and it's encoded in excess 127. So let's quickly show how it's done. Excess 127 to decimal conversion. 0 corresponds to negative 127. So we need to figure out what 1111 1110. Okay, so this is 126. All right, how do you do that? Well, you can do the number bases is one way of doing it, right? The powers of 2, or you can say, well, this looks like 128 or 127 or 126, because if we did this, again, a lot of different ways of doing it. We know that this is 128, right? 1, 2, 3, 4, 5, 6, 7, 8. And then you subtract 1 from it, we know that this is 127, right? And if you subtract 1 from that, you get 126. So don't worry, I'm not going to test you on how you do it. As long as you get the right answer, I'm not too picky about it. Okay, so know that this is 126. So if it's 126, I need to move in this direction. I subtract 127 if I'm moving to the right. So this would make me negative 1. And that's what I have over here. So the exponent is times 2 to the negative 1. Okay, so now all that's left is figure out the fraction. The fraction here is 100. That's my fraction. But remember, there's a hidden 1 I didn't have to encode. So it's actually 1.100. And that's what I have down here. Okay, I can get rid of the extra zeros because I can put infinite number of zeros after it, it would still be the same value. So I just decided, you know what, I'm just going to write it as 1.1. All right, and that's how you end up with the answer down. All right, let's do one more example. All right, so given this example, I want you guys to try this out first by looking at the sign bit, the exponent, and the fraction. Give you a few minutes to work on this, and then let's go over the answer together. Okay, let's try and do this together. All right, so the first bit is 0. So I know this is positive. And then the exponent is is 0 is negative to 127. This is 1 0 0 0 0 0 0 1. This is 128 plus 1, so it's 129. So moving to the right, you subtract 127 from it, so this becomes 2. So I know that this is going to be times 2, okay, to the 2. So now the fraction is 1 1 0 0 0 dot 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 0. But remember, there's a hidden 1, so it's actually 1 point. All right. So are we done yet? Technically, no, because it's asking you to convert to a decimal, right? This is still in scientific notation. So if I really want to be thorough and convert it, then this times 2, I move the decimal point 2 places. This becomes 1 1 1 dot. Okay. And 1 1 1 is 7. All right. Everyone got that?
Can you go over it again from the
Go over
beginning?
which part? I'm not going to go the whole thing.
Yeah, can you just re-explain it one more time?
All right. This is a sign bit. It's 0, so it's positive. This is the exponent. That's right here. This is encoded in excess 127. So this is excess 127 to decimal conversion. If you drew this table like what we did in the last class or 2 classes ago, then it's just figuring out from my left to my right. So first I need to decode 100001, and I realize this is 129. So it's 129 in my left column. Moving to the right column, I have to subtract 127. So it's 129 minus 127, that'll give me a 2. So that's where this is, okay? And that gives me my exponent. So all that's left is a fraction. So the fraction is 1100, which is this. But I have to add the hidden 1, which is this part. And once I have that, then it's just how do I get from here to from this to this number? Is that move the decimal place twice, right? Because it says times 2 to the 2, which means this goes 2 places. And I end up with this. And 111 is binary for 7. All right.
Thank you.
All right, next. Okay, so now we're going to move backwards. So now assume I have a number, negative 5.5. And I want you to encode this into a single precision float. So the first thing you need to do is convert to binary. So this is negative. 5 would be 101 is 5. And 0.5 is this, 0.1, right? Remember our number bases? This was 1, this is 2, this is 4, this would be 1/2, this is 1/4, remember that? So 1/2 is 0.5, right? So it's going to be 0.1. All right, so once I have this, the next step is to normalize it. This becomes 1.011 times 2 to the 2. All right. So once I have that, then let's start encoding this. First, I have, let me clear up some room here. My sign bit, my exponent, and my fraction. So the sign bit is going to be 1 because it's negative. And now my exponent, let's figure it out, excess 127 to decimal. This is 0, corresponds to negative 127. And now it's 2, so I need to go in this direction. So moving from right to left, I have to add 127, right? So this is 129. But this needs to be in binary. So I encode 129. 129 is 128 plus 1. And that's 129. So I put that here. Okay. Now all that's left is the fraction. And when I want to encode the fraction, I just encode this, right? I don't do the 1 in front of it because it's a hidden 1. So I just need to encode what I highlighted in yellow. So this is 0, 1, 1. and I pad it with a whole bunch of zeros. Okay, if you'll see me write it like that because I don't want to draw out 19 zeros. You know, that's the reason I just put dot dot dot. This just means that we know there's a whole bunch of zeros there, and that's going to be sufficient for this class. All right. So now I want you to spend a few minutes, try to do this one on your own. 13.25. Please encode that into a single precision float. Okay, so let's do this one together now. So 13.25. So 13 would be binary be 1101. So that's 13. So 0.25 is 0.01, right? Because the first, let me just make sure you see this. If this would be 1/2, this would be 1/4, right? So that's why it's 0.01. It's a quarter. And now I need to normalize it. So this normalized becomes 10101 times 2 to the 123 to the third. Okay, so now let's draw out our bit pattern. So this is positive, and the exponent is 0 corresponds to negative 127. So we have 3, this would be 130, right? So 130 is 128 plus 2. So this is 128 plus 2, okay? So that would be 130. And now the fraction. So remember, we only want the fraction, not the hidden 1. So this is only 1, 0, 1, 0, 1, 0, dot, 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 0. All right, and you're done. Okay, guys, give you one more, and then I think you guys have a good handle on this. All right, this one's a little bit harder, so give you guys a few minutes to work on this. Okay, let's do this one together. All right, so 7 is 111. 0.75, this is 1/2 plus 1/4, right? So 1/2 plus 1/4, it will be this. So now we normalize it, and this is negative 1.1111 times 2 squared. All right, now we're going to encode this. Sign bit is 1 for negative, and let's figure out what the exponent is. So this is going to be 0 to 127. So it's a 2, that would be 129 over here. Okay, so 129 is going to be 128 plus 1. And now the fraction is just this, right? Everything to the right of the decimal point is the fraction. So we'll write 1, 1, 1, 1, and then pad it with a whole bunch of zeros. Done. All right. Okay, so moving on. Now let's talk about range and precision. So let's talk about what range is. Range means the smallest value to the largest value. So if we had exactly 32 bits, a float is 32 bits. And the largest float you can represent is written here, right? Write out positive, and then we write this is the largest exponent that you can have, and this is the largest fraction. So that is equal to positive 1.11 times 2 to the negative 1, 2 to the 127. The largest int, however, that you can encode is when you set all 32 bits equal to 1. That value is roughly equivalent to 1.111 times 2 to the 32. So you might notice that, hey, why the difference? How come this is so much larger, even though it's the same number of bits is used, right? It's not like we instantly had 1,000 more bits. It's still the same 32 bits. Then how come the largest number is so much bigger? It's not 90 times bigger, because 2 to 32 times 2, if you double the size, is 2 to 33. So it looks like you're doubling it 90 times. So it's a much, much, much larger number. So the question is, how are you able to do that if you only have 32 bits? And the answer is that I'm giving up the ability to represent every single number in order to represent a large number. So let me show you what I mean. So let's start off with the easy case, when the exponent is set at 0, right? So decimal point doesn't move. So the exponent is set to 0. I have the first number is 2 times 2 to the 0 is equal to 2. The second number is 1, 1, right? It looks like they're 2 and 3. So when the exponent is set to 2 to the 0, I can represent every single number in sequence or contiguous. Now, this next set, all I did was change the exponent to 1. Okay, that's all I did. But now I'm multiplying by the same number, times 2 and times 3. Look at the result, 4 and 6. Notice that when the exponent is set to 2 to the 1, you can no longer represent the value 5. Can't be done. Once the exponent is set to 2 to the 1, you no longer are able to represent the value 5. Okay, do you see that? All I did was change the exponent. I didn't change the fraction, I just changed the exponent. Now, if I change the exponent again, I increase it to 2 to the 2. Look at the number. Now it looks like, look, you see the gap between the numbers? Now I'm not able to represent the values 9, 10, or 11. Do you see that? So as my exponent increases in size, and how many bits do you have for your exponent? You have up to 2 to the, oops, hold on a second, times 2 to the 120, 127. Okay, so the exponent can get very, very large. So what does that mean? That means that at that largest exponent, you're going to have huge gaps between numbers. That's why you're able to represent very large numbers, because you can't represent every number in between them. So that's what's called trading precision for range. I'm no longer able to represent every single number. However, my smallest number and largest number are extended at the expense of losing the ability to represent things in between. All right. All right. So if that is the case, what happens when I want to represent a number like 20,000,001? And you find that you can't represent 20,000,001 in single precision because you don't have enough bits to do it, because your fraction is only 23 bits, but once you factor in the hidden one, essentially it's 2 to the 24 bits, so it's roughly 16 million. Any number larger than 16 million, you have to represent by increasing the exponent, right? Times 2 to the whatever. But the problem is, you multiply anything by 2, you end up with even numbers. You don't. So look at this number. This is an odd number, ends in a 1. So you multiply anything by 2, you end up with an even number. So what this tells you is that using a float, you are not able to represent 20,000,001. You can't represent any odd number over 16 million. So how do I represent larger odd numbers? That's where doubles come in. Okay, so let's quickly take a look at doubles. So a double is almost just like a single precision float. The difference is the number of bits involved. So you have a signed bit just like before, but now the exponent is not 8 bits, now it's 11 bits. So because it's 11 bits, it's not 127, it's XS 1023. And then now there's 52-bit fraction. So both the exponent increased and the fraction increased. So let's go through an example of how to encode this. So negative 5.5 would be negative 101.1. And then I normalize it, it becomes negative 1.011 times 2 to the negative, I'm sorry, times 2 to the 2. Okay. So now encoding it, now here comes a difference. It's 1023. So 0 corresponds to negative 1023. And now I have 2 here. So 2 coming in this direction, you add, this is 1025. So writing out my pattern here, the sign bit would be 1. The fraction would be 1025. 1025 is 1024 plus 1. So 1024 is one of the powers of 2, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There you go. That's 1025. And then the exponent is just like before. We just want that 0 on 1 and pad it with a bunch of zeros. But with the understanding that the fraction has 52 bits, I just really don't want to draw out 52 zeros. Okay, so I just put dot, dot, dot. And then we're done. All right, now let's give you guys a chance to do a double. So again, almost identical to single precision float. You just got to remember that there's more bits involved and the excess encoding is 1023. All right, give you like 2 minutes to work on this. All right, so let's quickly do this together. 13.25. So this is the same from earlier. So I'm just going to quickly go do this. You can always look at the prior slides. But 13 was 1101 and 0.25 was 0.01. And then normalizing it, again, this is the same number, same exercise from earlier. Now that we're at this point, now let's talk about the differences. In excess 1023 to decimal, 0 corresponds to negative 1023, right? So now what we want to do is, oh, by the way, this is times 2 to the 123. So we want to go in this direction, right? So doing this, this is positive, and this is 1026. It's 1024. I'm 1023 plus 3 is 1026. And then I know that it's 1024 plus 2. Okay, and that's 1026, or binary for 1026. And now the fraction is just going to be this. Is 10101 and a whole bunch of zeros. All right, so exercise-wise, it's pretty much the same as single precision. The only real difference here for that was different from a single precision float is, got to remember that the exponent is 11 bits and not 8, and it's excess 1023. All right, so now let's talk about the special cases. I mentioned at the very beginning that the exponent is anything except all zeros, all ones. The reason for that is because this is what we've been doing all night, where this is the normalized floating point number. However, we have, when the exponent is all zeros or ones, those represent special cases. All right, let's quickly go over them. The first column at the top, or first row, the exponent is set to all ones. So when the exponent is all ones and the fraction is 0, that represents a concept, infinity. So you're actually not calculating anything with it. It just represents the abstract concept of infinity. When the exponent is all ones and the fraction can be any number, that's not representing a value. It represents a concept again, not a number, or represents an error condition. So this is very similar to in C++, you have a variable equal undefined, right? So this is just a way of indicating there's an error. Now, when the exponent is all zeros, the other case, when it's all zeros and the fraction's all zeros, that represents a value 0. There's only one instance where the exponent is all zeros and the fraction is all 0. So you have 0. All right, that leaves us with the very last thing for tonight. The last topic is denormalized numbers. A denormalized number is one where the exponent is all zeros and the fraction is non-zero. So what does denormalized mean? Denormalized means there's no hidden 1 because we didn't normalize the number. So it's denormalized, and the exponent is fixed at 2 to the negative 126, which means you don't need to calculate it. It's fixed at 2 to negative 126. So let's go through this exercise. The first number, first thing you should look at any floating point number is look at the exponent. The exponent is all zeros. So it's either going to be 0 or a denormalized number. So the next thing I look at is the fraction. Oh, it's not all zeros, so it's denormalized. So denormalized very quickly means that the exponent is fixed at times 2 to the negative 126. Okay, no calculation necessary. Now I look at the fraction. The fraction is 100, right? But guess what? There's no hidden 1. So it's 0 in front, 0.100. Okay? So that's the first number. The next number, look at the exponent. It's 1. So this is going to be doing the excess 127 to decimal conversion. 0 corresponds to negative 127. 1 is going to correspond to negative 126. So this is also times 2 to the negative 126. But now the fraction, if we look at it, is 100, but because it's normalized, I put a hidden 1 in front. Okay, so that's the difference between the two numbers there. The top number is a denormalized number with no hidden one. And the second number is a normalized float that has a hidden one. All right, that's it, guys. Any questions? All right, if there's no questions, then today is Thursday. I guess we will not see you until Tuesday, so have a good weekend. And actually, you guys don't have class on Monday, right?
Yeah, we don't have class Monday.
All right, so I don't have class either, so enjoy a long weekend, guys. All right, have a good one.
Professor,
Professor, question.
Yes.
what's
Uh,
the deal with the worksheets? Do they have like a due
Yeah,
date or
that's what I was
something?
asking.